All right, hello. Today we're going to discuss a theorem of geometry called the Inscribed Angle Theorem. So let's take down the proper statement here. Okay. So what is the Inscribed Angle Theorem? What does it suggest? So, supposing, well, let's do this first. Supposing one has circle chords OA, let's call with a prefix subscript 1, OA, and O1B, okay? Notice they share a symbol in their names, and so they have a common location on the circle. Then the angle formed, let's call it A O1B, will be half of the corresponding angle AOB, okay, where O is the center of the circle. So for our purposes, just so we have something to attach to in this moment, I'm going to draw a very quick diagram of what this is. Okay. Ooh, looks like I changed the size of that circle midway. Okay. So we're going to, this is called the central angle, but if this is O, and this is A and B, and there may be many O1s, who knows exactly where, that if I have the angle AOB, okay, I will know every one of these guys, which is quite miraculous. There's one. Wow, this one's pretty close to this, isn't it? Okay, and finally, we'll do this guy. That's better. And I'm going to limit myself to, if we split this into AOB, interior and exterior, I'm really only going to select from this larger arc here for the time being. I also want us to notice that there is a certain partition. Now, it isn't necessarily important for us to recognize that as the theorem holds for anything on this greater arc, if you will. But I do want us to notice that there is two sections. There are two sections, rather. And that we're going to have to make this distinction here between the highlighted region on the greater arc. Oh, I didn't go all the way. Okay. So there are inscribed angles which belong to this kind of mirror inscribed arc. And then there are regions which are, I don't know how to say it exactly, but which are not part of that, right? But still part of the greater arc. Okay. So what is our theorem again? We have some angle dot, black dot, and that if we know black dot, we know red dot, and vice versa. Notice there's an expansion of information from black into red, and there's a contraction of information from this infinite set of elements into the central angle, which may not be relevant now, but perhaps later. Okay, so let's go ahead and actually carry out this proof. Okay. So to start with, I'm going to draw us a diagram, and our diagram is going to select a particular inscribed angle from roughly within this region. Again, we'll make it more clear why we're going to do that after the fact. So, I do want some space to write. That's perfect. And again, we're going to use very, very, very simple information about circles and triangles here to help us. So we have the center of our circle. And I will arbitrarily select 2 points A, B. Again, I could have chosen anywhere. Doesn't matter where. And we will draw radius from the center O to the 2 locations. Okay. Remember, this is O. Now, making sure it's within those 2 angles, I select a 3rd point, and I will label it as I did before, O prefix 1. And I'm going to label these with different colors. And I'm doing this because when we move to the second half of our proof, it will be useful for us to kind of keep track of. So we go sub 1O to A, and sub 1O to B. Okay. Of course, this new shape is perhaps not so familiar to us. That's okay. We'll ameliorate that with this red pen. O1, sub 1O to O. Okay, great. So, in a funny way, we have a triangle, well, I should say an isosceles triangle, AO, OBA. We have an isosceles triangle, O sub 1O B. And we have a triangle, O sub 1O B, A rather. All 3 of which are isosceles triangles, right? So I'm going to label these angles quickly. And do I want this? I do want that. I am going to draw the final chord here so as to construct the isosceles AOB. There he is. Okay. So we'll call this theta. We'll call this A and A. Remember from our last video, we can be sure of this. I'm going to call this guy phi and N and N, right? Again, it's an isosceles triangle. Radius, radius, 2 equal radii. These must be the same. Okay. And C, SCE. I call it that. That's my own symbol. Again, this and this are equivalent. Call this M and M. Okay. So we have our initial construction, and we have some, well, simple information here. We know that we're dealing with a bunch of isosceles triangles in this particular case. And we've labeled all of our angles by some symbols. And well, we can go further, right? There's actually more information here than is just, well, there's more apparent information. Firstly, all three of these triangles, their angles must be 180 degrees in total, or pi. So let's go ahead and record that in a collection of equations. Okay, we know that. Let's do this guy. Phi and n. Phi n plus n. And finally, what did I do? Oh, theta. Theta plus alpha alpha. Okay. Great, so we have some information here, which kind of captures requirements of triangles individually. There's actually another thing we have here, right? We have a circle. We have rays coming from the center of a circle. And so altogether, what should their sum be? It should be this guy. Okay? And then our final claim, right? The claim that the theorem is asking us to demonstrate is that m plus n, m plus n must be, what must it be? Half theta. That's what we like. That's what we're looking to demonstrate. Okay, so let's ask the question. We want somehow to combine information here in such a way that we arrive at m plus n being something, right? That would be kind of where we want to live. So let's look at these equations. Let's see. We have things. We have expressions, equal expressions, right? Expression is expression, right? And we have, because these things are numerics, we have additive and multiplicative equality of equations, right? So if two symbols are the same, I could add the same symbol to either side, make some kind of transformation or replacement, and arrive at new equations, right? Which must be held true, right? This is a sort of axiomatic, our basis, right? On which we can build new information atop. So I know I want m and n together as part of an expression. And I want that because, well, that's what we're aiming for, right? So you know what I'm going to do? I'm going to add these two equations together, okay? In effect, I'm going to add pi to both sides and transform the pi on this side into this. And we're going to do that because we're going to end up with m's and n's together. Let's do that. This and this. And I'm going to jump ahead here, but notice there's two m's and two n's, right? 2 plus n. And that's going to be pi and pi, 2 pi. So just give you a second here to verify. C plus phi plus m plus n plus n. Phi plus phi. M plus m. N plus n. Okay. So I've synthesized information here within our axiomatic system. In effect, we do know these are theorems of other axioms, Euclid's, but we know that this is the case. And what I'm going to do in a second here is because I'm noticing, oh no, I don't really have theta here, and I do need that, right? I need an expression which maintains not only m and n, but also theta. And you know what would be really good is if I had an expression of theta which also had c and phi in it, which I do, right? That's nice, isn't it? Okay. So we're on like a second layer almost. We have a second layer of information. We've took our basis, our axioms, and we've synthesized new information here, which must be true. Now I'll go into a third layer. Okay? And our third layer is going to use the additive equality of equations. Once again, simple. This time we're going to add the negative of this to this. Now why would I do that? Why would I do that? Well, I know that the right-hand side will become 0 because 2 pi take 2 pi is, well, that they're additive inverses, right? 2 pi and dash 2 pi must resolve to 0. Okay, I'm going to take this guy here, this 2m plus n. And of course, I'm subtracting this guy from him. In a funny way, we could do it either way, but it's immaterial. But look what happens. Through application of additive equality, I have phi plus dash phi. I'm subtracting. That's additive identity. Bam. Just like this. We have c plus dash c. They're gone, right? And what remains is exactly what we wanted, right? We have an expression which maintains theta and m and n. Okay, and here we go. I want not just an expression of theta and m and n. Well, of course, this simply does capture it, right? In order for dash theta, right, dash theta to resolve to 0, what must this equal? It must be equal to theta, right? Or by additive equality, right, I can add theta to either side. Okay? And finally, for our proof, we use multiplicative equality to multiply half to either side, and we arrive at our statement. There we are. End of proof. M and n such that all three of these things are true, it must be the case that the sum of the interior angles, these particular angles, in our inscribed, right, m and n, resolve to the particular inscribed angle we're looking for, so long as all three of these are maintained, then our theorem is true. Something unfortunate is going to happen when we escape the mirror version of our arc here, which theta subtends. Let's take a look. So this will be true anywhere in here. Notice if I select any point on here, our theta, phi, and c retain the sum to be 2 pi. If I go over here, I know that this angle, let's say it goes all the way over here, and this angle and theta altogether become 2 pi. But let's look what happens if we're not there, if we escape that particular region into one of these side regions here. Let's take a look. And I will do what I had mentioned I was going to do, which is try to maintain the corresponding colors. So if O prime is here, sub 1, I come over here. I need to construct a blue which goes from sub 1, to A, and I need to construct a blue which goes from sub 1, to B. Okay. So let's draw those blues in so we can maintain some semblance of sanity here. There's that. And the other blue. And finally, we're going to draw a red, which was from sub 1, to theta, or to our central point here, O. Okay. So I want us to notice that things considerably change here, right? We still have a couple, well, we still have a couple isosceles triangles here. Notice that this thing, our sub 1, to O, is still a radius, right? And so we have this nice isosceles triangle here. Notice that our OA, we didn't move that at all, but it still forms a triangle with O sub 1, and so a isosceles triangle is still maintained here. And then the final one, which is continues to be maintained, but I'm noticing I actually never used it here, did I? These things are here still, okay? So of course these particular triangles have all changed in some sense, right? If I have O sub 1B, O sub 1B, okay, so it's like this guy became this one. We have sub 1A, O sub 1A. Okay, so there's this guy. This triangle became this triangle, okay, and this one stayed the same. Okay, so I want to kind of capture some of these angles here. I know I still want this guy, right? This is the sub 10, this is the inscribed angle right here. That's the one we're looking for again. But it isn't m plus n anymore, is it? M is next to a red and a blue. And it's O sub 1A. So I know it's this triangle, right? This m becomes this much larger guy, right? Becomes this much larger guy. That's our m. Let's see, we have O sub 1B, O sub 1B. Okay, so n is like this one, isn't it? Okay, so of course the something is wrong again. Well, wrong here. Oh, not necessarily wrong, but the configuration of the system has changed in a meaningful way, right? So much so that this is not true anymore, okay? And really the big thing here is, let's take a look. A, O, O sub 1. A, O, O sub 1. Let's make this green. So this angle is what this guy, C, was, right? Theta has gone unchanged. Okay? And then we want phi, O sub 1, O, B. O sub 1, O, B. Weird. Okay, so what happened? Something funny happened. They're like almost overlapping now. There's like something funny happened there, right? And this is the critical piece here. The angles that we were working with earlier, phi, C, and theta, were in a configuration. such that this equation was true, right? And we'll find anywhere within this arc that this statement is true. Having escaped that region, this is not true anymore. And we must re-express our axioms so that they're all true again. Okay? Notice that this, where was it? Is it B O sub 1, or sub 1 O O? That's phi. So I think it's 360 minus this, right? If we had this guy, which is pi, 2 pi minus phi, then we could kind of play the same game where we add c, we can add theta, and add not phi, but 2 pi minus phi, and we get 2 pi, right? Because that's a full circle. Okay. It is getting a bit crowded here, so I'm actually going to redraw this, and we're going to relabel, and we're going to demonstrate the second half of this proof, right? We have carried out, we have an end of proof. This is actually false. This is not end of proof. End of proof for mirror to theta arc. Okay. All right, so let's turn the page, and well, we're going to do that again. So let us draw our circle again. Let's draw them a little bit higher this time. Could have gone higher. Oh well. Nice old circle. Label our point O, which is our center. We will select A and B, A and B, and we will construct the isosceles triangle associated to theta. We'll also label theta. And we'll call those really cool because they're on a circle. And so if, just so I don't draw a circle or draw our O, sub 1 O in the wrong location, I am going to draw a nice little dotted line to remind myself where not to put O sub 1, because we have demonstrated in the upper region already that it is true up here. Okay, so let us select a sub 1 O in the region without less. This is a it's a reflection. O sub 1 O in here. We will draw our two blue lines, right? One to O sub 1 O A, sub 1 O A, and one to sub 1 O B. Okay, and finally, and of course that's the angle we're looking for, right? And then we'll use a red to go sub 1 O O again. There he is. Okay. So this is theta right here. What was that guy? That would be C. Okay. And then for our purposes, we do know that there's this guy here, right? And remember, O sub 1 O B. O sub 1 O B. That was phi, but that was on the interior, which is now the sum of these two, right? Theta plus C must be this. But just so I have it labeled, I'm going to write 2 pi minus phi out here. Okay. I'm going to try and use the same letters. So with C we used M. With C we used M. m, and this whole thing here, right, is m. Theta, we use alpha, or a, and a. Look, there's overlapping. It complicates things, doesn't it? And then finally, for phi, which is the sum of these two guys here now, is going to be n. Okay, so let's take down some information again. We know that, again, phi plus n, c plus m, and theta plus alpha are, they all are equal to pi, right? Conditioned on they're all the angles of a triangle. Let's take those down. I have to be honest, I haven't done this on paper yet, so we're going to see where we land here. I might over capture axioms, just like last time. Actually, I didn't even use this. Right, this was this theta alpha equals pi. I didn't even use it. Right, that's fine. Theta alpha. Again, I suspect we're not going to use this, but I'm taking it down anyways because any axiomatic information, even if it's too much, right? It's a maybe not an optimal or minimum set of information to get what I want. It's fine. Who cares? We're gonna arrive somewhere nice. And then phi n. Oops. Bring it down. There we are. Phi n plus n equals pi. Okay, so now some new stuff, right? I know that c plus theta plus phi, phi plus theta equals phi, right? This angle and this angle completely construct phi. So I think that might be something good to write. Let's write theta plus c equals phi. That might be interesting. And in fact, it's wholly distinct from what we had before. And I know this might be good to have. I want the angle A sub 10B, right? That's the corresponding inscribed angle to the central angle AOB, right? And that is what we want to eventually relate to each other. Therefore, at least in how this looks, it looks like m minus n equals the angle I'm looking for. A sub 10B is the angle. Okay, and again, I don't know why I wrote the angle there, but I know that m minus n, what we want to prove, right, is that it's equivalent to theta halves, right? This is our main statement that we really want to arrive at, right? This is the inscribed angle that we're looking for, and we want it, we would like to prove this is true, that it's half of this with our new information, like before. So it does look like I did more than I should have. Again, I don't think I'm going to use this. Oh well, it's fine. So let's start combining things and see if we can land somewhere. It's not entirely clear. I think there may be something happening here which will be very helpful, but I'm not sure. Okay. Should have prepared. What if I add these two again? So we're going to go c plus phi plus 2m plus n. So that's not quite what we want, right? That's not equals 2 pi. I don't really like that. Why don't I like that? I don't like it because I know that the angle, as expressed through the isosceles triangles we've constructed, is going to have to be m minus n. So this just straight up summation of the two first equations it's not great for us, is it? Let's do something different. Maybe there's going to be something better here. What if I subtract them? Now, I'm going to subtract them because it's going to arrive us at m minus n this time. If I go first equation minus the second, or minus the third here, that might be better. So we'll go c minus phi plus 2m minus n, right? M minus n. No, I really like that. Okay, but something's going to change here, is it? It's going to be pi plus pi's additive inverse, right? Dash pi. We're going to get 0. That's nice. That's nice. That's nice. I like that because it's m minus n, isn't it? Okay. So here's what we're going to do now. I am going to subtract c from both sides of this fourth equation, and then reverse distribute -1 from it. So it's gonna kind of feel weird here, but I'm gonna write negative am I going to do that? I'm not going to do that. I'm going to write theta plus phi, c minus phi equals 0. Sorry about that. That was not clean at all. All I've done here is done an initial transformation, which is subtract phi from either side, right? Additive equality. Okay, so now I actually really like this. I really like this. Why do I like this? If I subtract this synthesized, well, this transformed form from our axiomatic elements, subtract this from this, right? Subtract this from this. We're going to get cancellations again, and we're going to remove information about phi and c, which is what we'd like. And what remains is 2m minus n, the angle I'm looking for, right? We demonstrated that. M is this whole angle here, corresponding to this isosceles. N is this partial angle here, which is in this isosceles. And so their difference will give me the inscribed, the inscribed angle. So subtract no corresponding components in this from this. This subtract this, 0. This subtract this, 0. And we get minus theta equals 0. How funny. How funny is that? Okay. Whoa! So here we are. 2m minus n equals theta. And finally, m minus n, the angle we're looking for, the inscribed angle, is half theta. End of proof. Okay. So that's it. We know that every inscribed angle, for every inscribed angle, the corresponding central angle is twice it, or the inscribed angle is half of the central angle. So I hope you've enjoyed this proof. We will be back for more triangle constructions in our next video. Thank you.